My name is Min Hong. I am an economist at the Institute for Policy Integrity at New York University School of Law. Welcome to our webinar on energy disruptions and resilience. The Institute for Policy Integrity is a nonpartisan think tank dedicated to improving the quality of governmental decision-making. We produce original scholarly research in the fields of economics, law, and regulatory policy, with a primary focus on climate and energy policy. This webinar is part of a series highlighting environmental and energy research projects. We want to thank the Alfred P. Sloan Foundation for its financial support on this series. Our goal in these discussions is to highlight cutting-edge research on energy and environment, while also fostering connections between the research and policymakers' real-world needs. To achieve this goal, each webinar features academic researchers supported by the Sloan Foundation, as well as policy experts actively engaged in these fields. Today, our topic is energy disruptions and resilience. Climate change is causing more frequent and severe weather events that threatens our power grid and other infrastructure. It is crucial to understand the impacts of these failures, how to prevent them, and how to strengthen the power grid and other infrastructure overall. Now, transitioning to our agenda today, we have two parts. First, we will hear presentations from 4 speakers about their research projects or regulatory challenges they face. Afterward, we will have a Q&A session where our panelists will be available to answer the questions submitted through Zoom. Now, without further ado, I am delighted to introduce our panelists today. First, we have Dr. Duncan Calloway, who is a professor of energy and resources with an affiliate appointment in electrical engineering and computer science at the University of California, Berkeley. He is also a faculty scientist at Lawrence Berkeley National Laboratory. His research group focuses on emerging energy technologies by quantifying their impacts on power system operations and developing control, optimization, and data analysis tools to facilitate their integration into power systems. Next, we have Dr. Mikhail Chester, who is the director of the Mattis Center for Infrastructure and Sustainable Engineering at Arizona State University, where he runs a research program focused on preparing infrastructure and institutions for the challenges of the coming century. His work spans climate adaptation, disruptive technologies, innovative financing, cyber security, and modernization of infrastructure management. We also have Dr. Erica Fisher, who is an associate professor of civil and construction engineering at Oregon State University. Dr. Fisher's research interests revolve around innovative approaches to improve the resilience and robustness of structural systems affected by natural and man-made hazards. Dr. Fisher performs research on a variety of different structural systems subject to hazards such as earthquakes and fires. Last but not least, we have Luan Tesfaye, the California Public Utility Commission's Deputy Executive Director for Energy and Climate Policy. Luan has worked at the CPUC since 2011 in several roles and in the CPUC's Legal, Energy, and Administrative Law Judge divisions. Luan's experience includes renewable energy markets, siting and permitting generations facilities, and commercialization of clean energy technologies. Welcome, and thank you all for joining us. I am excited to delve into today's topic with our panelists. In the meanwhile, we also encourage our audience to submit your questions through the Zoom Q&A feature anytime during the presentation. Our panelists are excited to answer them during the Q&A session. Now, let's get started with Duncan Calloway, and then each panelist in alphabetic order by last name. Duncan, please.
Thank you very much, Min Hong, for the opportunity to be here. Today, I'm going to do just a high-level overview of a few different projects that I've been participating in that have been supported by Sloan, as well as a couple of follow-on or one follow-on project it was really very much enabled by the Sloan support that we've had. And all of these have to do with resilience and reliability work that we've been doing at Berkeley. So I'm going to start just by setting up something, what I call the power systems trinity, a way of thinking about some of the major trade-offs that that grid planners and operators and regulators have to think about on a variety of different timescales. So there's an economics objective, of course, that anybody who's regulating or operating the grid is thinking about, which is we can think quite simply as just delivering power to customers at least cost. Reliability and resilience objective, which is to maintain something that's both socially and politically acceptable for a level of reliability and resilience. And then environment and policy objectives, which is using, historically, actually in the very early days of power systems, it was using resources efficiently. It is transitioned more appropriately so to minimizing environmental impact and ensuring equitable distribution of costs and benefits across customers. So these three different objectives often stand in tension with one another. The cheapest possible system you could build is one with very low reliability, for example, and one that potentially pollutes quite a lot. So we are always looking for solutions that balance these things. One of the things that I think is quite exciting about the last decade or so of electricity infrastructure is that low-cost renewables have enabled more alignment, and maybe not perfect alignment, but more alignment of the economics and environment objectives. That is, we can now get very low-cost power production and delivery with renewables that are also not directly polluting. However, reliability and resilience is something that I think we need to pay even more attention to than we have in the past. So we have challenges like with more production from variable renewables and demand uncertainty, often coming from climate change and heat waves. There's potential for a misalignment between the availability of generation supply and what electricity demand is. And there's also a growing need for climate adaptation, wildfire risk, grid hardening, and so on. So these reliability and resilience things are factors that we spend a lot of time thinking about in my research collaborations, because we think that we can only achieve a sort of renewable, low-cost, sustainable power system if we can also simultaneously ensure that resilience and reliability are continue to be as good as they've been in the past. So I'm going to talk really just kind of like one-slide summaries of a few different projects that we've done that are Sloan funded and enabled. I just want to give thanks and appreciation to Sloan Foundation for two projects that I've been a part of. One with Jim Bushnell at UC Davis on evaluating distributed energy resource impacts on California utility distribution systems. And if you just look at this figure over here on the right, some of you, this would be familiar to you, but we can think of power systems in terms of generation, transmission, and distribution, the sort of final mile of delivery. And I'll talk a little bit about our research thinking about especially the capacity of these individual distribution feeders to deliver power to customers. And then we've also done some work in collaboration with Catherine Wolfram, who's now at MIT, and Fiona Burlig at the University of Chicago, thinking about power system outages and wildfires. This here is just a chart showing the growth in outage events over the last few years. Many of these outages driven by a desire to reduce wildfire ignitions from electricity infrastructure. So I just want to talk really quickly about distributed energy resource impacts on distribution systems. So in California, at our Public Utilities Commission, DER defined as batteries, solar PV, electric vehicles, and building electrification all sitting on the customer side of the meter. Too much DER can do things like trigger upgrades, needs for upgrades in distribution infrastructure, cause power quality issues at high or low voltages, for example, could degrade reliability if infrastructure upgrades can't support newly connected DER, and could also lead to denials of request for other customers to connect more DER. There could be equity implications here. So this is sort of like a high-level motivation for a number of the things that we're thinking about with respect to distributed energy resources. And some of the work that we've done in this space has been evaluating how much capacity circuits in Pacific Gas and Electric territory have for new DER. In this case, on this slide, we're specifically thinking about electric vehicles and building electrification. And what the top chart shows you is an assessment using extremely rich utility data of how many of Pacific Gas and Electric's electricity feeders will need to get upgraded in a 2030, 2040, and 2050 timescale. Just for context, PG&E has about 3,000 circuits. It's quite a big system. And what we're seeing here is that practically every single one of its feeders or circuits will need to get upgraded over the next several decades. If you look here, this red line shows their historical rate of upgrading their infrastructure, how many projects they do in a given year. And you can see based on our forecasts going out, could be, or it's possible, even likely, that the amount of work that needs to get done is quite a bit more than what has historically happened. So the concern here is if people keep electrifying transportation and buildings, there could be service denials, there could be outages resulting from equipment overload, unless PG&E supply chain and workforce is strengthened to the point that it can actually do all of these projects. So there's some really, I think, very important both policy, legislative action that's happened in the last year or so, but also the California Public Utilities Commission is moving forward with something called the high DER study, a phase 2 of that, where utilities are thinking on 10-year timescales about how much work they need to be doing under a variety of different load growth scenarios. So there's been some really exciting movement in this space. Another question we've been thinking about is, will all communities have equal access to this distribution grid capacity? So if you look over here, this is just a chart of a Southern California Edison service territory, showing you colors that indicate how much capacity for new distributed energy resources exists for different customers. Again, this is using SoCal Edison's primary data. The key thing I want you to take away from that chart over there is that it's quite heterogeneous. And anytime you have sort of spatially heterogeneous resource availability, you have the potential, because we live in segregated societies, we have the potential for inequities. And indeed, what we've seen in our work is that based on the data that we have available, communities that actually have more Black and Latinx residents actually tend to have less capacity for new DER per household. We don't have a causal explanation for why this is the case, but it still signals that there are important planning objectives to ensure that we have equitable access to distributed energy resources going forward. I think I'm going to start running out of time here pretty quickly, so I'm just going to very briefly describe this project that we've done. I've done with Fiona Burlig and Catherine Wolfram, where we've observed changes in reliability for customers based on public safety power shutoffs that have been done in PG&E, again, service territory, to ensure lower wildfire risk. So we actually see these very distinct spatial patterns and reliability that are centered on distribution circuit boundaries. And so we've actually leveraged that distinct discontinuity in space to try to understand how it affects people's, this is on the y-axis here, outage hours versus distance from a feeder circuit boundary. So we've leveraged that to try to understand things like, do people buy more battery storage in response to improve their reliability? And we see that in rural areas, there is a statistically significantly greater propensity to purchase energy storage for reliability purposes, but we don't actually see a significant change in metropolitan and suburban areas. And then finally, I just briefly want to talk a little bit about some work that we've done, follow-on work, thinking about wildfire risks and mitigation strategies that utilities in California use. So this is a map of several thousand ignitions that have happened over about 5 years, the little maroon dots there that are utility infrastructure caused. And we've been able then to also look at all of the efforts that PG&E, again, in this case, are using for things like public safety power shutoffs, fast trip circuit enablement, covering their conductors, putting conductors underground, and managing vegetation. And we've again leveraged variability in space and time to estimate causally what are the impacts of those different mitigation measures on reducing ignitions. And here's just an example of the kinds of results that we have, where we actually have found that in terms of cost, dollars spent per avoided ignition, a new innovation called a fast trip setting, which is essentially just a very sensitive circuit breaker, is extremely cost effective at reducing power system caused utility ignitions. However, it is not 100% effective. So we find that it's cost effective, but only reduces ignitions by about 70%. So there's another 30% of ignitions remaining that those fast trip settings can't actually avoid. The main takeaway that we have here is that there are these really important risk-cost trade-offs that we think regulators and utilities need to be thinking about. The alternative is undergrounding infrastructure, which eliminates a vegetation-caused ignition risk, but is far, far, far more expensive. And so there are important societal decisions to be making around these kinds of investments. So I'll go ahead and stop there so that the next panelist can do their presentation.
Thank you very much, Duncan, for the great presentation. Now let's hear from Mikhail.
Great, thank you. And full screen. All right, thanks all. So Mikhail Chester, and I'm at Arizona State University today. The high, according to my phone, is 109 degrees Fahrenheit. And we will experience in my power utility a couple hundred outages, small scale, which is the usual norm with this high heat relative to maybe just about a dozen in the colder temperature. And today I'm going to talk to you about how we think about and prepare for surprise. And I'm going to sort of present to you a number of projects that we're doing that focus on how you have challenges, generally climate related, that manifest in power systems that ultimately make their way to other systems, not simply to elucidate the challenges of coupled infrastructure systems, which I think we know well, and there's many people working on, but to talk specifically about a few challenges that we have in dealing with the growing complexity of the systems, the lack of data, the unpredictability of the behavior of these systems, and also how we might co-govern across these systems, ultimately to protect a power system by investing elsewhere. So I'll start by giving recognition to the Sloan Foundation that has enabled a lot of this work. Today I'm going to focus on a lot on Phoenix and New York City, where we've done a lot of the Sloan work. We have a patent pending on some of the models that I'm showing you. And there's been a number of NIST and NSF projects that have also supported this work over time. So as I mentioned, there's a lot of teams that are focused on this question of, coupled infrastructure and what that means, even, climate hazards, how they manifest in one system and ultimately make their way to another. And yes, indeed, those are major challenges, and there needs to be a community of folks working on this. But in general, the challenges that we focus on is one, when you do vulnerability assessment, whether it's social vulnerability, infrastructure vulnerability, economic vulnerability, or otherwise, you need local data really to understand the true nature of what's playing out. And often we're dealing with coarse data with infrastructure. For example, power transmission tends to be somewhat available, although patchy at times. Distribution tends to not be available, right? So here I'm going to talk about a little bit the synthesizing of data and how we might plug in some of those gaps. Next is complexity, and I use that word specifically. Complexity is different than complicatedness. A complex system is one where there's many characteristics, but of particular importance is the emergent characteristic. The emergent behavior of the system is largely unpredictable. And when we look at these coupled infrastructure systems under a climate hazard, for example, complexity reigns. It's very difficult, to know what's going to happen. We know if we hold a hurricane over New York City for a prolonged period of time, something bad's going to happen, but precisely what, where, when, why, how, if anybody tells you they know, right, they're probably, there's probably some hubris there. So we have to embrace the sort of unpredictability and surprise inherent with the growing complexity of these systems. And lastly, often we deal with this challenge. I've been having lots of conversations after a New York Times article 2 days ago on, could Phoenix be a Katrina of extreme heat? So, yes, it could, right? That's the short answer. But, there's a much more challenging discussion that needs to happen around, one, how we prepare for very high consequence, but very low probability events. Many people might say, very, very low probability is not going to happen on my watch, or, very unlikely. So I don't need to steer the very limited resources that I have towards that problem. I'm going to focus on, for example, the more moderate probability events that have lower consequence, something along those lines. So as we shift towards, again, climate hazards, complex systems, the interdependence of these systems, right, we become increasingly aware of and concerned with these very, very high consequence but low probability events. So where we focus, if there's sort of one thing I want to get across from our Sloan work and related projects, are these challenges right here. I'll show you guys some of the particulars and empirical results related to the modeling, but I actually think this is the slide here that really captures the essence and nature of what we're trying to do within our team. So one is, real versus realistic, getting at this question of how good do the data need to be in order to do something? Does it need to be perfect? How precise, right? So often there's a set of questions where we need true data, and there's this different set of questions where, realistic, good enough data, gets us an answer that's actionable and cost effective. Second, is how do we understand the nature of these cascades within and across infrastructures? Because to be resilient, it may make sense from a power perspective, for example, to make investments in non-power systems to protect the power system. I'll give you two obvious examples. One, if I want to protect my power system against forest fires, it may be more cost effective for me to hand that money over to a forest management agency for things like forest thinning and vegetation management. I might get more and better results investing in forest management than I would in directly investing in power, right? And it's not necessarily binary, but we can think that way. Another is, if my system's vulnerable to flooding, it might be more cost effective to invest in stormwater, hardening or not the stormwater system to prevent that flood from happening than it is to actually harden, elevate, do whatever it is, move, build redundancy in my power asset, my substation or otherwise. I already talked about low consequence, high probability events, how to protect one infrastructure against another, and then this idea of general versus specific adaptation. So I'll show you guys results for flooding in Phoenix and New York City. Phoenix has a monsoon season. Yeah, it's hot right now. At the end of the summer, we're going to start getting monsoons, essentially tropical storms that hit us, wind, lots of rain, and associated flooding from that. So, New York has hurricanes. Should we protect Phoenix the same way we protect New York? In some ways, yes. In some ways, no, right? So we think about those differences. And then also, how we might identify common failure patterns. So I'm going to show you guys results here in a minute that show how, if we insert unpredictability into the system in terms of what the operators do, in terms of what a climate hazard might do, right? Run 1 million scenarios, or I'll show you 120,000 scenarios. It's somewhat paralyzing to think about the deep uncertainty associated with that. But what if we start to see certain patterns emerge? Then we actually might be able to, make focused efforts in terms of what we're doing. So generally what we're doing is we're using either true or synthetic data. We have synthetic models that we've developed, everything from power transmission to power distribution, also on the water side and stormwater side. We're coupling those systems. We're using flow solvers. So, we can use, Pandas Power, PyPSA on the power side. We'll use things like EPANet or PC Swim on the water side, whether it's drinking water or stormwater. So we're actually trying to solve the system as it's being perturbed. We're then capturing these interdependencies, not simply that a pump in a water system requires electricity, for sure, that we would call a direct interdependency. There's actually 4 types of interdependencies, right? But another would be geographic, right? So if you have a flood that takes out a substation, for example, that's a geographic interdependency we want to capture. So we do, we're going to derate things. So for example, you push a monsoon through Phoenix or a hurricane through New York. How do we trip a transmission line? So what's the probability of failure given the particular wind speed, given what it's rated at? And then fundamentally, we're going to do stochastic exploration of state spaces, again, to get at these sort of common failure patterns. But, if we look at lots of different iterations, do we see common failures? And the answer is yes. So in general, this is what our model does. And, we try to use true data where we can. We often don't have it. And by the way, it's not simply because of security reasons. When we deal with military installations, for example, we're not always working on cities. Often, you'll get somebody who says, I want to give you the data, but it doesn't exist. It's not digitized, or, it's not even on a piece of paper. We know that there's probably lines under the road, but we don't know precisely where or what they are because they were put in 80 years ago. They've been maintained, upgraded since. We just don't know. Right. And then other times we have data, but it's patchy and it's problematic, right? So in particular, I think of the DHS HSIP data set on transmission. And in newer places of the US, like the US, the data is better. In older places like New York City, it tends to be actually quite problematic. So we'll synthesize there. So here's an example of what we might do. This is 100,000 feet, folks, and I'm just going to quickly go through kind of some of the ways that we approach these problems and what it is that we might see. So here we're synthesizing a transmission network for Phoenix on the left. We're synthesizing a water distribution network on the right. We do validation and all of that. And then what we're doing is looking at particular transition line thresholds in terms of when they might trip, which is based on a number of different characteristics. And we'll start with N-1, 2, 3, 4 contingency failure models, where we'll say, what if one transmission line, or we could do a substation, goes offline, then repeat with 2, repeat with 3, repeat with 4. And this could be random, or it could be intentional, based on, for example, a monsoon coming through, wind speeds that we might have microclimate information on, and we could fail things in precise ways. And ultimately, we'll then say, okay, what happens? Well, out of 120,000 iterations, what we start to see on the left there are 31 common failure patterns of substations going offline. So more often than not, the system's just fine, which is what you would expect. In about 10,000 iterations, you'll see about 3,200 failures or so. More often than not, the system is hard, robust, armored, strengthened, robustness type strategies where it's totally fine. But we also start to see scenarios where they fail. So here's an interesting one to look at. Power's on the left in red, water on the left in blue, and then green is power and water. So here's something interesting to take away. Almost never do you see concurrent geographic regions where the exact place where power is offline is the same where water is offline. By the way, that's a water pump that's been affected by a substation that's offline, and then you're having insufficient pressure in the water system. That's the blue. So almost never do we see the same geographic areas that are offline, right? So that represents sort of a triage problem in terms of how you manage this. Okay, and we do see these black swan events emerge. Here you have roughly a quarter of the city that's without electricity. And, you see articles like this emerge. This is about a year ago from the excellent work of some of my colleagues and folks at Georgia Tech, Brian Stone, showing what would happen if there was a prolonged large-scale outage. And again, not to say that this isn't going to happen, but we can actually start to describe how you would get there, and more usefully talk about how to prevent that from happening. So similar work ongoing in New York City. You've got we run our models here where we're essentially pushing a hurricane through the city, and a Sandy type hurricane through the city, or even just nuisance type rain events, and kind of running our model to say not only what's affected infrastructurally, but similar to what was previously shown, we're overlaying sociodemographic data, ultimately describe the demographics of who's affected, and ultimately where you might prioritize resources. And lastly, it's not simply power to water. Here we have models that capture the relationships between stormwater and transportation back and forth. So with stormwater, it's not simply that power knocks out a stormwater pump, for example. It could be that stormwater knocks out power. You have a flood that knocks out a substation, for example, or you've got transportation failures that prevent you from getting resources to power assets when you need to rehabilitate them. So we can start to capture those sorts of dynamics in our model. So this is, again, backed by PyPSA, PC-SWIM, as well as some of our transportation flow models. So hopefully that gives you a perspective, and if you guys want to see some of the readings that and publications and reports and so on, you can go to this website. Thank you very much.
Thank you so much, Mikhail. Next up, we have Erica, who will share her expertise on infrastructure resilience to natural hazards.
Hey, thank you so much. And hopefully this segues well from the other two presenters. Just like everyone else has said, giving thanks to the Sloan Foundation for allowing us to really explore the wildfire impacts to water infrastructure. This grant is in collaboration with CU Boulder as well as University of Minnesota, and looking at sensor development. But I'll try to give an overview of why we're looking at this. And some of the work that we've been doing in integrating this into policies at the local level, state level, and federal level. So, you've heard a lot about wildfires, and I do want to just preface for those people who don't study hazards all the time. Wildfires are actually a natural occurrence within our landscape. It is actually quite beneficial for our flora and our fauna to have wildfires occur. And so we don't always want to suppress them constantly, but we end up with complete disasters. This is a photo I took in Paradise, California after the 2018 Camp Fire. And so when does this happen? And the last two presenters focusing on power and water systems is so critical, because we call it a disaster. Obviously there are federal financial definitions to this, but from a disaster science point of view, we're really looking at loss of community functionality, and the utilities, the water, the power are so critical to the functionality of a community, as well as the healthcare systems and educational systems that we've seen when we study hurricanes and earthquakes and other hazards like that. And we've seen this for decades and decades, that when we lose these systems, we see our communities are less resilient. And so we really need to protect these systems and harden them and be able to create adaptable systems to these changing hazards, so that when these fires do impact our communities are able to recover. And so in wildfires, though, we kind of have this other part, because you constantly hear about single family homes. And so the way that it connects the two is our homes are simultaneously the fuel for the fire within the community. It's not the vegetation within the community. The fuel for the fire in the community are the homes. They will release about 10 times more energy in the fire than vegetation. And they will burn for substantially longer and threaten all the homes within a 1.5 kilometer radius of them with embers. So they're simultaneously the fuel for the fire, but also the assets that we're trying to protect. So when you hear a lot about wildfires, you're hearing a lot about single family homes and protecting single family homes. And we don't want to lose them, because that's going to have an impact on the tax base and customers for businesses. But it's also because they are the fuel for the fire. And so if we are not protecting our single family homes, the fires can overload fire response. And then we see what we're seeing throughout the Western United States. All right, so I'm focusing, this project is focusing on water infrastructure, but I just want to prime you to why we're focusing on water infrastructure. So, and the role it plays within that community. And so I'll give you all kind of a little crash course on water infrastructure here. And so you have your water main, which I'm kind of showing down here, and that's usually buried over a meter deep below the surface of a road. These are the big pipes you might see driving along the side of the highway. Then you have what's called a service lateral that connects to a water meter. Here in the West, we have our water meters at the curb. They're not on our house itself. And then we have another service lateral that connects the water meter to the house. So when we talk about wildfire impacts to water infrastructure, we're really talking about this service lateral that connects the house to the water meter. Since the water meter is not on the house itself, the pipe needs to rise up to the house level. And as it's doing that, and when the house is on fire, is being heated, it is thermally degrading. And what we're ending up seeing is they're seeing volatile organic compounds within the water distribution system after the fire. And we've seen this in many different fires. We've seen this in 2017 Tubbs Fire, 2018 Camp Fire. We saw this in every single town impacted by the 2020 Labor Day fires here in Oregon. We saw this in Lahaina, and we saw impacts to water infrastructure as well after the 2021 Marshall Fire. So this is happening over and over again. We're seeing pipes melt. We're seeing this have a huge impact on the recovery of the community, both with time as well as with cost. And we're seeing this really impact our businesses. Over on the right, this is a photo I took outside of a restaurant in Paradise, California. And so you can't boil volatile organic compounds out of water. And so if a restaurant wants to reopen, they need to be using bottled water for their cooking, as well as serving. So this is a huge burden on communities to get their businesses back up and running, their economy back up and running, reopening schools, reopening hospitals, and just attracting people back to the community, right? People really don't want to move back to a community that doesn't have potable water. They don't want to send their kids to schools in communities that doesn't have potable water. So it really has a trickle effect throughout the community. And so the way that this is happening is that when our homes are burning, it's really heating up everything around it. And we're seeing these homes are burning for, 2 hours or more. There's a lot of fuel there. So if they're burning down, they're burning for quite some time. Heat is being transferred into the soil, and it's being transferred to the pipes itself. In the West and in a lot of the United States, our pipes are plastic. So they're PEX pipes, PVC, HDPE, and these pipes are really durable. They're very cost effective. As Mikhail mentioned, there's trade-offs in all of your decisions with your utilities, and having cost-effective pipes and really durable pipes is really beneficial for the community. However, these pipes are going to thermally degrade and release volatile organic compounds. At the same time, when our homes are completely burnt down, what ends up happening is because there is so much demand on our water distribution systems for firefighting during the fire, we'll see local depressurization of the water distribution system. Ash and soot will be drawn into the pipes. And then what will happen is either you will thermally degrade the pipe from the inside out because it's hot air coming into the pipe, or the ash and soot gets circulated around the water distribution system. And we already know that this ash and soot has a lot of volatile organic compounds that we're seeing within the service laterals. This heat transfer mechanism has been studied by a number of researchers, including our group, throughout the country. And we've seen that it does actually produce the volatile organic compounds that these communities are finding in their systems. But we've yet to, our group has just simulated this depressurization experimentally to be able to isolate these two contamination mechanisms and see how they are contributing to the contamination that these communities are experiencing. And so, how does this kind of go into policy? And, first and foremost, in 2021, I helped the EPA pull together and develop some sort of guidelines for communities, but they're very vague. It says to uniaxially flush the system, collect water samples for testing, stagnate that water within the community, within the system for a period of time, but they don't really specify, and then collect water samples and continue and rinse and repeat until you don't have any contamination anymore. What ends up happening is most of the communities just end up replacing all of the service laterals because they cannot get rid of the contamination. And so there's a lot of questions with this that have motivated our research is where should the municipalities collect water samples systematically? And this really goes towards understanding where we're going to actually see this this contamination, even though you don't have the data. As Mikhail mentioned in the last presentation, you don't always have data for every single piece of utility. But also, sometimes you don't have time to collect all that data. We also understand, where the asset mapping within our communities. What are the most important components of our communities, and where should we be testing our water so that those components can actually recover and get back online? Why are more samples categorized as contaminated after stagnation? It's a huge question that we have. And why does flushing not solve the problem? And I'm going to kind of go through all of this. So what we've been doing, and I'm just going to kind of go through conclusions from a lot of the work that we've been doing, is first and foremost is we developed fragility functions to actually correlate contamination with burn severity in a community, defining burn severity as density of damaged structures. So we're able to actually show in Paradise as well as in Santa Rosa that we see a higher probability of exceeding the federal or California maximum considered limits for these compounds when we have higher density of damaged structures. We also see the same thing for backflow for that depressurization. And so just showing that shows that, where do you test after a wildfire? Well, where you have high density of homes is probably where you want to test first. We tested all the pipe materials to determine at what minimal temperature do we begin to see actual contamination leaching from these pipes into the water, so that we can actually see and correlate that to a real fire. Can an actual fire cause this contamination? And so then we perform numerical analyses, putting a fire in a house, and then look at performing heat transfer analyses through the soil to look at, can we actually cause contamination to happen given these critical temperature thresholds? And we actually can in these pipes. We saw that metal pipes actually did not cause any contamination, and we tested those as well. Then lastly, we actually burned large compartments down and then simulated that depressurization to examine just how are these pipes having contaminated water inside of them with this depressurization mechanism. And we're seeing that this ash and soot really adheres to the inside of these walls, causing a buildup and causing a lot of contamination. And that even in metal pipes where we see contamination in the air, we're not actually seeing it in the pipes themselves. All right, so quickly, I'm going to run through how this all kind of translates into policy. At the local level, we actually helped the city of Louisville recover after the 2021 Marshall Fire, developing sampling plans for them, as well as where to actually cut off and shut down the system post-fire, so that they could get the rest of the water system online for the rest of the community that wasn't damaged. We've worked with the Oregon Health Authority. They've been mapping out the damage from the 2020 Labor Day fires. We just a paper that we wrote with a bunch of the water districts was actually published 2 days ago, summarizing the response to these fires in all of these different areas, as well as what the recovery efforts looked like. And then federally, this has been now actually acknowledged in the National Cohesive Wildland Fire Management Strategy as a huge problem post-fire that needs to be focused on, and that needs to be front and center, that our water infrastructure is not immune to damage from our wildfires. I just want to thank the rest of the project team, obviously the Sloan Foundation and many of our collaborators outside the project team, and of course all of the grad students sponsored by the Sloan Foundation. And we have a website if you want any more information. Thank you very much.
Great. Thank you so much, Erica, for the insightful presentation. Just a quick reminder to our audience, feel free to submit any questions you may have through the Q&A feature. Now let's hear from Luan, who will provide regulatory perspective on today's topic.
Great, thank you so much, and thank you for including me on this really important and insightful webinar. My name is Luam Tesfaye. I'm the Deputy Executive Director for Energy and Climate Policy at the California Public Utilities Commission. I did want to start by telling you a little bit more about the work of the California Public Utilities Commission. So we are an agency in the state of California that is governed by 5 commissioners. And we are located in San Francisco, Sacramento, and Los Angeles, given our statewide jurisdiction. The California Public Utilities Commission regulates energy utilities. That includes electric utilities and natural gas utilities. We also have regulatory oversight of water utilities, as well as telecommunications and broadband, as well as transportation, including rail safety, as well as vehicle safety for entities like Lyft, Uber, and autonomous vehicles. So we have a very broad regulatory authority. As the Deputy Executive Director for Energy and Climate Policy, I lead our Energy Division staff. So we have about 230 staff that are working across the state on issues including integrated resources planning, energy efficiency, general rate cases and financing of utility operations, microgrids, transportation, electrification, and more. And so it's a very broad oversight over the work that utilities are doing in the state of investor-owned utilities are doing in the state of California, as well as our load-serving entities that are procuring electricity to serve customers in California. So I wanted to start my remarks by talking a bit more about transitioning to California's transition to a clean energy future. So for California, electrifying our economy and decarbonizing the grid are key components of our climate change leadership. California has long led the clean energy transition, and with 59% of the state's electric retail sales generated by renewable and zero carbon resources in 2021. In addition to that, climate change is also causing unprecedented stress on our grid. So as you can see from this slide, California does have very ambitious climate goals of 90% clean electricity sales by 2035, and then 95% by 2040 and 100% by 2045. But this doesn't mean that we don't still see the unprecedented challenges from stress on our grid, and particularly from climate change. We are being impacted by extreme heat, by drought, by flood, and wildfires, and they are increasing in frequency and intensity. And this has become a very real threat to reliability and resilience of the energy systems in California. We know that the grid of the future is one that is clean, safe, affordable, and reliable. And it's not really a question of if, but how we transition to our clean energy future. And I think that the presentations that you just heard from Dr. Callaway, Dr. Chester, and Dr. Fisher really highlight the different work that's going on nationwide to help support this important work for our country. So after hearing all of those great presentations, I've been taking notes and thinking about all of the different areas that the California Public Utilities Commission is working on right now to address these threats to our electricity grid, and the many stakeholder processes that people that are listening today might be interested in participating in or learning more about. I did want to take a step back before jumping into that to just talk a little bit more about the Energy Division at the Public Utilities Commission and our vision. So as I mentioned before, the grid has to be clean, safe, affordable, and reliable. And so that's really the North Star of all of the work that's done in the Energy Division at the Public Utilities Commission, whether you're working on microgrids, transportation electrification, or integrated resources planning. And so that's really our North Star, and we're really trying to balance and achieve all 4 points of this North Star. Innovation has long been a cornerstone of the work that we're doing. And so a lot of the work that we do is cutting edge, and some of it does have risks, but we do think that the larger risk is staying stagnant. And we know that we have to keep moving forward in order to be able to address these energy challenges. And then finally, I did want to highlight that diversity, equity, and inclusion and environmental and social justice is a cornerstone of all of the work that we do. And it's a focal point of the innovation that we're working on here in the Energy Division. California is a very diverse state, and we know that in order to reach our clean energy and climate change goals, we are going to need to be able to engage every single customer in California. In addition to that, we do know that the impacts of climate change, grid disruptions, and the need for resilience impacts our disadvantaged communities the hardest. And so as we take all of these steps forward, equity is a focal point of the work that we do. And the California Public Utilities Commission has adopted an environmental and social justice action plan to help us stay focused on those equity concerns that come up in the work that we do on all parts of energy and climate change. So first I wanted to talk about the work that California has been doing on wildfire mitigation and how that has dovetailed with the investments that we are putting into our grid. So wildfire mitigation, when it comes to grid investments, have included a very large and diverse suite of strategies. So vegetation management, which had been mentioned by an earlier speaker, is a very large component. And vegetation management is one that our utilities are required to do around the energy infrastructure. And we have codes and standards that they work towards in order to make sure that vegetation around utility infrastructure is kept at a minimum and as safe as possible. In addition to that, we are also making many investments in the grid, whether it's undergrounding infrastructure, covered conductor, as well as grid enhancing technologies to enhance the safety of the grid. As Duncan mentioned in his presentation, as Dr. Calloway mentioned in his presentation, California knows that we have very extensive amounts of grid enhancements and work that have to occur on our distribution system to be able to accommodate transportation electrification, as well as building electrification. And we do this work all within the auspices of the scoping plan that the California Air Resources Board has adopted. So the California Air Resources Board continues to adopt regulations for zero emission vehicles and is also working on further regulations related to zero emission appliances. And so we need to make sure that our investments in the grid are preparing us to be able to meet those different regulations that are being adopted by our sister agencies. In addition to that, we want to be able to further accommodate enhancing economic growth for California, as well as very important needs related to new housing for California. Housing has been a longstanding challenge in California and has been a priority for our governor. And so we need to be able to both enhance the existing grid as well as expand the grid to be able to accommodate further economic growth in housing on our system. And so what we've been trying to do is make sure that as we continue to make investments to support wildfire mitigation, making sure that those same investments are helping us with accommodating zero emission vehicles, as well as building electrification and other distributed energy resources that customers and communities are investing in. I also wanted to talk about how we are enhancing the resilience of our grid through integrated resources planning. So California adopted an integrated resources planning through Senate Bill 350, which was adopted a number of years ago. And so the integrated resources planning process ensures that we are able to meet our greenhouse gas reduction goals that I talked about on an earlier slide, while also making sure that our system stays reliable. And the California Public Utilities Commission works very closely with our sister agencies at the California Energy Commission, which does the demand forecast, as well as the California Independent System Operator that does our transmission planning in order to enhance our work to reaching 100% clean energy in California. But we have observed in the last few years a number of challenges, in particular related to climate change, but also supply chain during the COVID pandemic that created additional reliability challenges on our grid. And so through that process, California has also invested in what we call our Strategic Reliability Reserve, which is a reserve of resources that is being managed by all of the energy agencies in California, including enhancing the number of batteries on our system, enhancing technologies like demand response that we've invested in for many years, but being able to enhance it further by putting more technologies on our grid to make those resources more reliable and make them go further. In addition to that, the Strategic Reliability Reserve has also adopted emergency load reduction programs, as well as demand-side grid support programs through the Public Utilities Commission and the Energy Commission, which are enhanced tools and compensation mechanisms to get customers to reduce their use in the event of an emergency. But since then, California has been able to make great strides with bringing more resources onto our electric grid. Just looking at 2023, we were able to bring an unprecedented number of new resources to the California grid at over 5,700 megawatts in 2023. So those types of acceleration of new resource build out has been really key to help enhancing the reliability of the grid. And California has had to create additional stakeholder processes and tools for developers, like our TED task force, which is helping to build new electricity generation and helping developers get through permitting challenges, as well as interconnection challenges to bring those new resources online. And that has been a key part of helping to make our system more reliable. Now, shifting from integrated resources planning, I did want to also highlight the work that we've been doing in the area of microgrids to enhance resilience to the system. So microgrids are not a one-size-fits-all. Not all communities need microgrids, and not all communities can accommodate a microgrid, because they do take upgrades to the system. But in 2019, the Commission opened a new rulemaking focused on microgrids and resilience. And through that process, we've been able to streamline interconnection processes to help communities build microgrids. In addition to that, the Commission adopted a $200 million microgrid incentive program for California, which we are in the process of launching, which really focuses on disadvantaged communities and the most vulnerable communities, ones that have had significant shutoffs, in order to be able to support them financially in building microgrids in those communities that have the most resilience challenges. I also wanted to highlight another rulemaking that the Commission opened in 2018 and continues to do work, which is our climate adaptation proceeding. So the Commission has a long history of investing in climate adaptation research, and we really started doing that through our electric program investment charge, which is a unique ratepayer-funded research and development program in California. It created research and development programs at the California Energy Commission, as well as within our three main investor-owned utilities, Pacific Gas and Electric, Southern California Edison, and San Diego Gas and Electric Company. And so through those investments in climate adaptation, we've really been able to fund important research tools that are able to be scaled through the utilities to enhance their ability to plan and invest in their system in a way that is responsive to climate change. And since then, we've been able to adopt the California statewide climate change assessment as a baseline for our utilities to use for that investment and planning. And then our utilities have also started creating our disadvantaged communities and vulnerability assessments for the utilities in order to better be able to connect with their community, but also do long-term planning that's responsive to climate change, and so that they're able to adapt the climate. So with that, I wanted to turn it back to the moderators for us to go into our Q&A, but I hope I've been able to share a few different areas of work at the Public Utilities Commission that are really focused on being able to build a more resilient system. I also wanted to close by Just always sharing that the CPUC's Energy Division is hiring. That QR code will take you to our recruiting page. We are hosting another virtual open house on June 13th, where people can learn more about the positions where we're recruiting. And we're always looking for new perspectives and new skill sets to join our Energy Division. Thank you.
Thank you, Luan, for the great presentation. All right, now we are about to start the Q&A session in a minute. If you still have any remaining questions, please feel free to submit them through the Q&A feature. And in the meanwhile, I want to invite all the panelists to turn on your cameras. And now diving into the Q&A session. Okay, thank you. I will jump in first with a few questions, starting from Luan with a reverse order. So Luan, we understand that to prevent potential disruptions in the future, regulators play a key role in forming those forward-thinking policies based on new technologies or latest research. My question is, can you share your experience regarding how regulators use new research findings and new solutions to create such policies? And also, how do you see academic institutions contributing to this collaborative process? Thank you.
Great. Well, in quite a coincidence, Dr. Calloway is actually one of the main researchers that the Energy Division has been working closely with, especially most recently in our high DER proceeding, which he mentioned, where right now we are working on a staff proposal that's out for stakeholder comment on how do we enhance our distribution planning processes. And so the California Public Utilities Commission has had a long-standing relationship with academic institutions, particularly in California, like UC Berkeley and UCLA, but then also through our electric program investment charge, that research and development program that I mentioned, we are also authorizing ratepayer dollars to go to a variety of institutions through the California Energy Commission and our utilities, in particular academic institutions. And so it's really those partners at the universities in California that are really able to help us hone in on the latest research, as well as helping us to understand how we can best incorporate that latest research and latest thinking into the challenges that we're working on addressing in California and at the PUC.
Thank you for that, Luan. Let's move on to the next question, which is for our three academic researchers, Duncan, Mikhail, and Erica. You're all esteemed engineering experts in different fields. So we know that as energy systems become more complex, we need insights from different disciplines like engineering, economics, public policy, and maybe environmental science to tackle these issues. So can you share your insights about how interdisciplinary collaboration can contribute to more comprehensive energy resilience strategies or other strategies to improve the general infrastructure resilience? I'll start with Duncan.
So it's one of the reasons that I work in on the electric grid is because it is fundamentally interdisciplinary. And so in my case, I've been really fortunate to work with some incredible economists and policy experts. And, you know, I would say that there's a piece of infrastructure like the electric grid, as I set it up before, you know, cost, ratepayer cost, questions about sort of equitable distribution of cost and benefits are really, you know, that's in the wheelhouse of economists. But then there's this, you know, there's a lot of domain knowledge that engineers can bring to the table and modeling expertise that they can bring to the table. So it's in my case, at least, it's I suppose I've just deliberately moved into an area that is fundamentally interdisciplinary and just requires that kind of collaboration to actually have any real sort of, I think, insight, especially at this sort of policy regulatory level.
Thank you. I'd love to hear Mikhail's thoughts on this as well.
Yeah, so, you know, I think of the power system. We focus on lots of different infrastructures. Power is often, as you might suspect, central to many of them. But the power system is, you know, arguably the smartest of the infrastructures. And, that's by necessity, given the nature of the system that you guys are probably intimately aware of. It takes, we have a local water system here. One of my students, former students now runs it. And he says when they release water at the reservoir, they open the gate, so to speak, to control. It takes 16 hours on average before it reaches, the demand point, right? And power is obviously fundamentally different than that. And, I think that intelligence in the power system, whether it's intelligent enough is something else to talk about, but that intelligence that's there is often, I would contend, going to open up and is opening up the boundaries of what we have historically considered the power system to be. By that, I mean, you are seeing very quickly the integration of and the diffusion of the boundaries of what a power system is to become something else. So we're hearing examples of this, right? So, you've got arborists and the need for climate science, right? Economists, policymakers, right? Those exist for 100 years in power systems and every other infrastructure. But, a climate scientist, an arborist, a forest manager, what's Tesla? What are electric vehicles? Are those transportation systems? Are those energy systems? They're both. Can you design a power system for climate or any other challenge, ignoring the reality of emerging and disruptive electric vehicles to grid, having batteries in our house, pushing energy back in? Who controls that? Is it the power system that controls that? Is it the car company that controls that? Is it a third party, charger / controller in your home that controls that? Who's deciding how energy is consumed in a building if you have a smart thermostat, whether it's Trane or Google or any other company, right? So, these boundaries that we typically think of that define the system, I'm going to argue, are quickly unraveling. And I think we're at the beginning of what we're going to see to be a much quicker unraveling of who's in control of these systems, challenging the existing norms, which have typically been, often a single supplier, a power company, and the users, to something that's going to be far more complex. And I'm going to contend that the role of government is going to have to change to more fundamentally manage and build consensus within the complexity of who's in control of these systems.
That was very thorough and intuitive. Thank you. And Erica, do you have a different perspective?
Yeah, I think just to support what the other two panelists have said, to do this type of work, it has to be interdisciplinary. We've talked a lot today about power systems, about utilities, about the economy, but if we pull back, the entire reason we're talking about that is because they're important to the people who live there. And we are engineers, right? We're not social scientists. And so we need to work with our social scientists to understand how these communities function, not from an infrastructure perspective, but from a social perspective. Our job as engineers is to create infrastructure and study infrastructure and make it resilient so that it doesn't have a social impact when it's damaged, right? The best way of saying, talking about infrastructure is that no one notices it until it's not working. So we kind of operate in the background. When we're talking about wildfires, we're seeing our communities damaged more and more. And so now it's not just engineers and social scientists and economists and politicians, but we need to start engaging the Forest Service, land management agencies, as well as forest economists and forest managers. So, do we mitigate in the wildland? Do we mitigate within the bounds of the community? Do we do both? How much do we do of each? Where do we put our money? What's most effective? That becomes, all of a sudden the room grows more because we're involving more disciplines. It's the best case of interdisciplinary research. I think these disasters and these hazards don't know what the bounds are of communities. They don't know where one community or municipality starts and the other ends. And so we're seeing large land masses being damaged across jurisdictional boundaries. That means that multiple utility organizations need to be involved, sometimes multiple states, Sometimes these boundaries go from a socially vulnerable community into a non-socially vulnerable community. The kind of prime example is the Alameda fire in Southern Oregon. Started in Ashland, not a socially vulnerable community. They do wildfire mitigation, and it's spread to Phoenix and Talent, two communities that don't do wildfire mitigation that are highly socially vulnerable. So now you have regions involved, and so it becomes really complicated really quickly, and bringing all of these experts to the table is really, I think, the fastest way we're going to come up with some innovative solutions.
Thank you, Erica. I really appreciate your work on community engagement. I think that leads nicely to our next question. I would like to invite our speakers to share what you believe are the most pressing gaps in your understanding of energy disruptions and resilience. We know identifying these gaps is crucial for different stakeholders to work together to figure out solutions to improve our energy system resilience in the face of future disruptions. So for this question, I'll start still with Duncan.
I'll tell you the things that are on my mind, and these are not, I'm sure that there are going to be other answers, but well, case in point is right now that parts of the West are experiencing a pretty significant heat wave. We've had a number of, I would call them regional heat waves. We have yet to experience something that is really Western wide, or thinking outside of the West, something a climate event that impacts a very large geographic scale. And if we think about a lot of the motion, the movement that we're making in large-scale power systems design, it's increasing its interconnectedness to enable more resilience. I don't think we're thinking hard enough right now about the potential for a kind of all hands on deck situation where there's a very large regional event and we can no longer sort of rely on neighbors to provide support in those extreme situations. And then I also just think that we're this hinting at or sort of reflecting a little bit also on what I said about some of our wildfire work. I think we're moving into a world where we have to think much more carefully about the balance between cost and risk. And I would say that we're right now, we basically kind of, I feel like we're flying blind. We're trying to figure out what is the politically and socially appropriate thing to be doing to manage risk, but we're not quantifying it carefully enough so that we can really think about trade-offs. I think something that Mikhail said at the beginning of his talk, utilities are putting a lot of effort into mitigating the possibility of an ignition in their wildfire, in their infrastructure, but there may well be much more effective ways to manage the risk of some sort of damage to ecosystems, to infrastructure by, dealing with the fuels themselves. And so I think there's a lot to be gained by having a much better perspective on cost and risk, and then allocating our effort in the place where we're going to get the most bang for our buck. We're in a situation, though, where we have the privately held corporations that are publicly regulated, and there's firewalls between what they can do and what we can do from a sort of public funds perspective. And so I think innovation there is really critical. Trying to figure out how do we sort of reduce those barriers to thinking about our infrastructure more as a public good rather than a publicly or a privately held asset.
Thank you, Duncan. Next up, Mikhail.
Yeah, I mean, I 100% agree. And let me try to expand on that and sort of give you guys this question. So I presume there's utility folks in the audience here, and there's folks that just work with utility folks, right? And, let me just start with this fundamental question of, think about this. What are the governance agencies that manage power systems, whether federal agencies, private, public, at whatever scale? What are they designed to do? what do we need them to do? Whether it's climate, whether it's, EVs and battery disruption, whether it's aging assets, right? Think about it, right? So are they 100% aligned, right? Most of the governance structures that define power systems emerged like 100 years ago. And they emerged for a very different set of problems. And, here we are in 2024, talking about climate change, talking about equity, talking about sustainability, talking about resilience. And I'm far from convinced that the governance structures and the knowledge systems that they produce, remember, infrastructure systems are predominantly, or first and foremost, knowledge generating enterprises. You need that knowledge before you decide, what size transformer to put in, right? So what sort of knowledge are they ready to produce? What do we need them to produce? And I think this is what we call, I think there's a gap. When we call this gap, the gap between, or the decoupling, excuse me, between, what these systems are designed for and what we need them to actually do. And if you were to, get together with your colleagues over a beer or a glass of wine or whatever it is that you do, and ask on a, or draw on a napkin, right? Like, what would a, governance system handling power systems in 2024 look like? How would it be different? Would it have a divisional bureaucratic form, which is what you have today? Would it have something different, right? How would it be structured? What types of knowledge would it produce? And so on, right? I think these are the core questions that we need to ask. And that's not me saying, anarchy, blow up the system. That's me saying we need to rethink what type of knowledge we're generating and ultimately what type of knowledge we need going forward, right? And it's a very difficult question to ask. It's a very difficult question to sort of put into practice. There are examples of public agencies that have asked this question. It's not impossible, right? I find it fascinating that you're simply able to ask that question in the first place, right? Most folks in most public agencies are simply not able to ask that question, right? So how do you even begin to ask that question and ultimately open up space for yourself to be able to think organizationally about how you do things differently and ultimately what that means?
Thanks a lot. Erica, do you have anything to add?
Sure, I'll add 2 points. First and foremost, we need to be able to actually perform risk assessments for wildfires in communities that actually consider homes as fuel. Right now, every risk assessment that is out there does not consider homes as fuel. And so what this does is it doesn't allow communities to actually see how their risk can decrease with mitigation. We need that. That's super powerful for communities to see how much can they mitigate to decrease their risk, and where do they mitigate to decrease their risk, and whether that risk is risk to damage of the infrastructure, or risk to housing loss, or risk economic risks to the community, social risks to the community. We desperately need to be able to give this tool to our communities, and there's a lot of us doing research on this right now to be able to develop this because it just doesn't exist. And the second thing I'll mention is that there's the communities that we're seeing like it damaged heavily due to wildfire impacts are not Portland or San Francisco that has exceptional resources both in personnel and knowledge and money, but there are these rural communities in Oregon. It's our rural communities that are wildland urban interface communities, and they lack resources substantially. Sometimes they don't even have a formal water municipality. There aren't any full-time employees who are working there. And what that does is it burdens the community desperately. And it's really hard to recover when you don't have people who have knowledge on how to actually respond to this. And so being able to develop some sort of network so that these rural communities can actually be supported when these natural hazards make landfall.
Thank you. And Luan, we would love to hear your thoughts about this question, especially regarding the real world needs from the regulator's view. Thank you.
Yes, and I think the point that Mikhail was making is a really important one, and one that the California Public Utilities Commission had to undergo, I don't know, about 5-7 years ago and develop a whole new division called our Safety Policy Division that's really able to focus on these issues of risk, issues of safety culture, and they work very closely with my team that's focused on energy power systems, cost recovery, and investments. And I think also it's important that those two teams are separated. Granted, affordability is a very key issue, but being able to look a bit independently and ask those tough questions without being first focused on the price tag allows us to really be able to think outside of the box. And so that's led to a few different things in California. Now our electric utilities are creating wildfire mitigation plans, which is a way for them to work more prospectively in order to determine what type of additional work they need to do on their system, whether it is, and I think, and then it comes back to the Public Utilities Commission for us to be able to make those cost cross comparisons. So for example, and I think giving an example is really the best way to talk about this. So I think a lot of people working in the space have heard a lot about undergrounding. Pacific Gas and Electric Company has had large plans related to undergrounding. But in addition to that, like Duncan mentioned, vegetation management is a key strategy that has to be looked at. Vegetation management is not a capital investment. So, utilities are not able to earn a rate of return on those types of investment, but it has to be a key part of the work that they're doing. In addition to that, some people say that undergrounding is the panacea. It's the way to eliminate all risk. And one, I think it's important to remember you can't eliminate all risk, but first and foremost that. But second, there are also other strategies like, for example, covered conductor that have a very high probability of reducing wildfire risk and are actually able to be deployed much more quickly. You saw Southern California Edison deploy a very extensive covered conductor capital plan. And so that's also your trade-off is, undergrounding, moving earth, that takes a lot more time and money to be able to get that out there. And versus covered conductor is a strategy that is less costly and able to be deployed much more quickly. So you're able to get the benefit of the reduced wildfire risk much more quickly to support communities. And so those are the questions that I'll say, 10 years ago, the Public Utilities Commission was not equipped to answer those questions. And we've really had to shift resources around, build new teams, and leverage the research and academic communities to help us think differently about how we engage in this work.
Thank you, Luan, and thank you all. All right, we've had a productive session discussing the important topic, energy disruptions and resilience. It looks like our time is up. We hope to continue the discussion in the near future. Today's webinar is the last of our webinar series. We will post blogs and links to the YouTube recordings on the event page of our website. Before we wrap up, I'd like to express our sincere gratitude to our panelists today for sharing their expertise, to the Alfred P. Sloan Foundation for its financial support, and to all of you, our attendees, for your active participation and insightful questions. Thank you all for joining us today. We look forward to connecting with you again soon. Have a wonderful day.
Thank you.
Thank you.
Thank you.